the last lecture, we analyze a rotor with a single mass system, and we even considered single degree of freedom system, in which the difficulty is that we can able to get the response, but as we know that in a rotor the motion take place in two orthogonal plane. The whirling motion which take place we cannot able to represent with a single mass rotor system. So, today we will see another model, that is called Jeffcott Rotor model, in which we will be considering 2 degree of freedom system, by which you can able to analyze the orbit of the shaft also in two transverse direction, and subsequently we will be analyzing some other variant of the Jeffcott rotor, in which we will be considering 4 degree of freedom system. So, let us see the overview of the lecture, that is Jeffcott rotor model with 2 degree of freedom, then Jeffcott rotor model with an offset disk that will be having 4 degree of freedom system. In the previous first case, we will be considering only the linear, that is translation motion of the disk. In second case, not only the translation motion, but also the rotational motion, that is the wobbling motion we will be considering of the disk when it is especially offset in a simply supported case. So, some of the concept like wobbling of the motion and this avoidance of the critical speed, these concepts will look into this particular lecture. So, now a Jeffcott rotor model. In the previous lectures, we have come across regarding this particular model, in which there is a elastic massless shaft and the disk is there at the middle and bearings are rigid. So, if we look this particular rotor model, this is the bearing axis and we have a disk which is attached with a shaft, and the disk is at the middle of the shaft span, and the bearings are rigid. They are allowing the rotor to have rotary motion, but no transverse displacement take place. And if we see the axis, so this is x axis horizontal direction, vertical axis y direction, and accordingly we have z axis in this direction according to the positive convention. The rotor is having spin speed omega and is whirling about its bearing axis, the deflected shaft, at new frequency, but we are considering the synchronous whirl condition. That means we are considering the whirling frequency is equal to the spin speed, because main force which is causing here is the unbalance. Now, if we see the free body diagram of the disk, in xy plane, this is the disk. The shafts will exert elastic force, let us say ky, kx, where these are the displacements x and y, and this is the center of rotation of the disk. Let us say center of gravity is offset. So, we have, if our time reference is x axis, then this particular angle I am representing that as a theta, which is function of time, and theta is equal to omega t for constant speed, but at present we are not considering that as a constant. So, this is not equal to omega t. So basically in this particular case we have x, y and theta as the generalized coordinate to define the position of the disk, and now we can able to obtain the equation of motion by equating the force balance in x direction, y direction and theta direction. In this particular case, let us see the position of the center of gravity, which is here. CG is let us take as E. So you can able to see that position of the disk is the position of the center of gravity of the disk will be in x direction as x plus E cos theta, and in y direction its position will be y plus E sin theta. So this is the position of the center of gravity, and if we derivate this twice, that is the acceleration of the disk in x and y directions, and if we multiply by mass, these are the inertia forces. Now we need to equate this with the external forces. If we have damping also in the system, we will be having damping forces also along the x and y direction like this. So if we want to balance the forces in x direction, we will be having elastic force and damping force. Similarly in y direction, we will be having elastic force and damping force, and right hand side is the inertia forces. Apart from this, you will see that because at center of gravity mass mg is acting, so that will also come in the force in the y direction, that is in this particular case it will be minus mg. Not only it will give force, it will give a moment about the center of rotation. So if we take the force moment balance in the theta direction, this mg will give us a moment mg into E cos theta, that is horizontal component of the eccentricity, that is a moment arm, and it is acting opposite to the motion, that is motion in the counterclockwise direction, theta direction, and this couple is in opposite direction, clockwise, so it will be negative, should be equal to the polar moment of inertia of the disk, polar mass moment of inertia of the disk, and the angular acceleration. So these are the three equations of motion corresponding to three generalized coordinates. In this particular case of Jeffcott Rotor model, initially we started with 3 degree of freedom system, that is the 2 translational motion x and y, and 1 theta, that is a torsional oscillation. Generally this torsional oscillation and the transverse vibration coupling we neglect, and in this particular analysis also we will see we will be neglecting this by assuming the speed of the rotor is uniform, so that we can able to write the theta equal to omega t for uniform velocity of the rotor speed. Now these equations can be simplified by taking the derivative of the terms here, and let us see what it takes the form. So in this particular case, first thing I am taking is omega is equal to omega t, so that we have this as constant speed of the rotor. So the third equation is having no meaning now. The first 2 equations will give us equation of motion of this form. And in y direction, m y double dot plus cy dot plus ky is equal to me omega square sin omega t. So, you can able to see these equations are representing transverse vibration in x and y direction. As such, these two equations are independent of each other. They are not coupled equation. So, we can able to solve the equation separately. If you recall in the previous lecture, for single degree of freedom system, the second equation we solved it, and those solutions are valid here also for second equation also, because you can able to see rotor is symmetric, their properties are same. So, from the previous analysis we can able to write even the x displacement as m omega square e, that is the amplitude in the x direction. It will be same as y, it will be same as y because rotor is symmetric, is equal to y. So, the response which we write in the form of like this. There will be some phase also because of damping in the system. You will see that these can be written as and since x and y are same in this particular case, so basically it is representing a equation of a circle, because these two are same, equal to let us say r. So, this will represent the orbit of the shaft which is circular. So, if we plot the orbit of the shaft, let us say in x and direction, there is this will be circular, where this amplitude in x direction and y direction, basically they are same, equal to r. So, this is the orbit of the shaft center. These two equations we can able to combine in the rotor. Again I am repeating, the equations of motion which we obtain in x and y direction, they can be combined and they can be solved in a complex form, and this particular approach is quite popular in rotor dynamics. So, let us to understand that approach, we solve these two equations simultaneously. So, in this particular case we have two equations, again I am writing of this form, and in y direction of this form. Now, we defined a complex vector r which is x plus j y, and this particular vector, complex vector, we can use in the two equations by first multiplying the second equation by j and adding it to the first one. So, we would get these a combined equation in complex domain, and here we will get cos omega t plus j sin omega t, and this can be simplified as e j omega t. Now, the response can be assumed as a amplitude and is having some frequency that is coming here, and the phase also. Phi is the phase and R is the complex amplitude. If we take derivative of this, we will get j omega R j omega t minus phi. Another derivative, because in equation of motion we have two derivatives, we will get omega square minus omega square R j omega t minus phi. These assume solution and its derivative we can able to substitute in the equation of motion, and if we substitute, we will get equation of this form, that is m then omega square R, I am taking some of the terms common, plus c j omega R plus k R. I have taken j omega t minus phi as common, and that is equal to right hand side we have we obtained earlier m e omega square e j omega t. So, this was from the unbalanced force. Now, you can able to see the e omega t both sides will vanish, and we will left with this particular equation. I can able to simplify this also. I can combine the real part in one place and the imaginary part in other place, and R is common, j minus phi is equal to m e omega square. Time dependent terms will vanish now. So, this is separate. Now, we can able to expand this so that we can able to separate it out the real part and imaginary part. So, this will give us this is the expansion of the exponential raised to j phi is equal to m e omega square. Now, if we equate the real part and imaginary part, we will get expression, let us say from the real part. I am equating the real part at present, C is there. I am equating the real part, right hand side we have m e omega square, then imaginary part I am equating both sides of the equation. So, and in the right hand side there is no real imaginary part, so it will be 0. You can able to see the second equation, this is first, this is second. Second equation can be solved to get the phase. Tan phi can be obtained from second equation. So, this is Cw by k m omega square, and this we can able to substitute in first to eliminate the phi terms. From there we can get the R, then because R and phi are unknown, this can be written as if you recall, similar expression we obtained when we did the analysis with single degree of freedom system. Let us see these equations more carefully. We can able to non-dimensionalize these terms. Let us say I am defining a frequency ratio as spin speed divided by natural frequency, undamped natural frequency, where undamped natural frequency is root k by m. I am defining the damping ratio which is the damping factor divided by the critical damping, where critical damping itself is defined as 2 root k into m. So, using this we can able to write the tan phi, which was in the terms of the various parameters like k, m, c. It can be written as in non-dimensional form, and similarly the response ratio I am defining as the actual complex amplitude divided by eccentricity. This can be written as frequency ratio square divided by this expression. These expressions, now we can able to plot them. So, now this non-dimensional complex amplitude and the phase will be plotting, and this is the plot of that particular responses. You can able to see the horizontal axis is the frequency ratio in the first plot, and the non-dimensional amplitude, complex amplitude is in the second, and you can able to see it has been plotted for various damping. At 0 damping, it will be at very high amplitude will occur at the frequency ratio 1, but as the damping increases, this peak occurs slightly less than the this frequency ratio, because this frequency ratio has been defined with respect to the undamped natural frequency, and with the damping, the damped natural frequency will be slightly less than the undamped one. So, that is why these peaks are before the ratio 1, especially when the dampings are high. And you can able to see that as we are increasing the frequency, these amplitudes are going toward the value 1, because this for that particular case, this particular amplitude becomes equal to the eccentricity, and the rotor tries to rotate about its center of gravity instead of center of rotation c. And this is the phase plot in which various damping ratios have been chosen, and you can able to see that they all meet at 90-degree phase when there is a frequency ratio 1, even at 0 damping or very high damping case, and as the damping increases, they asymptotically. So, there is a change in the phase at critical speed. You can able to see of the order of 180 degree. The meaning of that is the response changes its phase with respect to the force, and there is a change of 180 degree. That means the unbalanced force which was outside, it becomes inside toward the center of rotation of the shaft, and because of that it tries to pull the rotor toward the bearing axis, and because of that we have smaller displacements as we are going toward the high frequencies. This particular Jeffcott rotor model, which we derived for 2 degree of freedom system, we analyze them using a complex variable approach. Now, the same problem we will be analyzing using a matrix method, because we will see that as the degree of freedom of the rotor increases, the matrix form is more convenient to handle. So, let us see in a very simple form how this matrix method is useful for handling these kind of equations. So, these equations we can able to write in matrix form, we can able to combine them, which we derived earlier. Like this, because we had 2 equations. So, this matrices are 2 by 2. this is a velocity vector, then we have stiffness term. As such, these equations are uncoupled, but to show the matrix method more detail, I am showing this for this particular simple case, but this analysis will be valid for more complex cases also. So, this is the unbalanced force. This also we have kept in the matrix form. So, basically this particular matrix we can able to represent in more compact form like this. This is a force vector. So, first one is the mass matrix, then we have damping matrix, and then we have stiffness matrix, and these are the inertia, velocity, displacement, and this is the external force. Now, this particular force vector, let us simplify them. So, I am writing this particular vector separately. Now, this can be written as, let us say, real part of m e omega square e cos omega t plus j sin omega t. So, that means we are interested in the real part only, the imaginary part just we are adding for our convenience. Then second is sin omega t, and here we are adding j cos omega t. Now, here I am adding minus, we will see what is the advantage of this, but basically we are interested in the real part of this. We can add the imaginary part any value, because here we are looking into the real part, we are not considering the imaginary part. So, this can be written then as real part m e omega square. First term can be written as j omega t, and the term which is below we can able to take out the minus j outside, and this can be simplified as minus j e j omega t. So, if we take minus j out from this, this will become cos omega t plus j sin omega t. So, we can able to write this particular expression. So, if we take minus j from here, we will get this expression, and now you can able to see that we are writing this as real part, let us say f unbalance in x direction and f unbalance in y direction, and j omega t is common. So, I can take outside. Now, we know that we are interested in the real part only, because in left hand side of the expression all are real quantity. So, even we can drop this term from this, and it will not make any difference, and where this f unbalance in x direction is m e omega square, and f unbalance in y direction is minus j m e omega square. Now, you can able to see that this is nothing but minus j equal to minus j into f unbalance in x direction. So, we have this relation for this particular case, and this is valid only for one particular direction of rotation of the the relation which we obtained in the previous slide, that is in y direction is equal to minus j f unbalance in x direction. This is valid for a particular direction of the axis and the direction of the rotation. So, in this particular case, this is x and y direction. Rotor is having whirling in counterclockwise direction. So, this center of rotation, this center of gravity, this is the reference axis. So, in this particular case, omega t is in this direction. So, you can see in this particular case y axis is lagging behind x axis for this particular direction of whirling. So, this particular expression is valid. If our whirling direction is opposite, that is clockwise direction, then we will be having this relation valid. In this particular case, our x axis will be, when in this particular case whirling direction is, let us say, in this direction. So, x axis will lag behind the y axis by 90 degree, which is taken care by the j, and minus j is the for the first case. Now, with previous slide analysis, we can able to write the equation of motion now in matrix form like this. And f amplitude and j omega t time dependent term is outside, where we have a mass matrix earlier defined as like this, stiffness matrix or damping matrix as this, and stiffness matrix K. Diagonal terms are there in all this, and unbalanced force, this particular unbalanced force we have as unbalance in x direction and minus j unbalance in x direction, because this is taking care of the 90 degree phase. Now, we can able to assume the response as a complex amplitude and the same frequency as the force. In this particular case, the phase is taken care inside the capital X. If we are considering, let us say, phase separately, let us say xr is the real quantity, and if we are taking the phase inside here, then this can be written as minus j phi, this can be brought inside, and j omega t. So, you can see now x bar is real, and but this quantity is complex. So, they can be combined and written as a complex displacement and E j omega t, and this particular thing we have written here, where x, capital X is the complex displacement, and this is the frequency of excitation which is coming from the unbalanced force. Now, once we have chosen the solution of this form, we can able to take the derivative, first derivative. So, we will get this, and for second derivative we will get this, and these solutions and its derivative we can able to put in the equation of motion, which is there in the matrix form. So, we will get solution like this. We can able to take the complex displacement vector and the force the time dependent terms e j omega t will vanish from both sides. And if we are defining these as, let us say, A matrix, then we can able to write this as simple equation like this. Our aim is to obtain the response of the system for a known unbalanced force. So, this can be obtained by inverting this particular matrix to get the response. So, you can able to see that we are getting the response using this equation, which is in matrix form. Here, sorry, this is capital, this is a complex displacement. This particular displacements will be having this form x real part plus x imaginary part and y component real part and its imaginary part. So, when we solve this equation, we will get two quantities, that is first one corresponding to the x displacement, second corresponding to the y displacement, and amplitude in x direction we can able to get from these components of real part and imaginary part by squaring it, adding it and taking the square root. Similarly, of the y we can able to obtain from this complex quantity. So, these will be the displacement amplitude in x and y direction. Their phase can be obtained, let us say phase of x displacement tan inverse x I divided by x r. Similarly, phase of the y direction displacement can be obtained as tan inverse y I by y r. So, we obtain not only the displacement amplitudes, also the using matrix method we have seen that is very convenient, especially if you are using some kind of MATLAB which can handle the complex matrices. We can able to solve the amplitude of vibration and its phase easily. Let us say, because at present we have illustrated the method using simple 2 by 2 matrix. So, I will show in more detail how these can be interpreted if we are trying to solve by hand calculation using the matrix using the matrix method. So, for illustration, I am taking the equation of motion in more simpler form, that is, I am taking only the mass matrix and I am neglecting the damping at present. And there is a forcing. These are the complex force amplitudes which take care of the phase also. Excitation frequency is omega, which is corresponding to the spin speed. Now, we can able to solve this. If we assume the solution, I am writing the expanded form. If you are assuming the solution in this form, where x and y are complex displacement, we can able to write the equation of motion with this assumed solution of this form. And so, here time dependent terms are getting vanished, they are getting cancelled out, here we can able to write this as, we can able to combine these two terms in the left hand side, and this will be something like this. Equal to the forcing in x and y direction. Now we want to invert this particular matrix to get the x and y. If we want to invert this matrix and multiply with the fx and fy, inversion is simple. Just we need to put this in this form. So this is the inverse of the matrix, this particular matrix. Now you can able to see that we have x is equal to fx divided by km omega square, and y also we can able to write here fy divided by km omega square. So this kind of expressions earlier we obtained, in which fx was me omega square. So you can able to see that how the matrix method works very conveniently. Only thing is, when damping is there, these matrices will be complex and need to be inverted in complex form. So we have seen the simple Jeffcott rotor model. There is a 2 degree of freedom model in which we neglected the torsional and the transverse vibration coupling. In this particular case, this particular model, as we see from in this particular model, the shaft is very flexible. The bearings are rigid here at the two ends, and the disc is at the midspan of the shaft. So when the whirling is taking place in vertical and in two planes, this particular disc always remains vertical, because this is at the midspan and the slope of the shaft elastic line is always 0 at midspan. So there will not be any tilting or the wobbling of the disc take place. But if same disc is at the offset, is not at the center, now you will see that when is at the midspan, when it is at the equilibrium, the disc will be vertical, but when the shaft is wobbling, the disc tilts. You can able to see during whirling it tilts about its diameter, and this particular motion is taking place in two plane. So continuous wobbling, this kind of wobbling will take place of this particular disc. In the previous case, when we considered the disc at middle, we could able to define the position of the disc by just x and y position. There is a translational motion, but when it is at the offset position, now we need to define the orientation of the disc also, because of its wobbling. So not only we need to define the two linear or the two translational displacement x and y, also we need to define the tilting of the disc about two axes, that is x and y axis. So here we will be having 4 degree of freedom or 4 variables to define the position of the disc, and this is the variant of the Jeffcott rotor, in which the disc is offset from the center. In the subsequent topics, we will see this particular kind of wobbling not only introduces additional degree of freedom, but also it introduces the gyroscopic couple also, because this particular disc is spinning about its own axis. Now because of this it starts wobbling. So there is a precession of the disc also along with the spinning, and because of that we find that gyroscopic couple will also be there. In subsequent lecture, we will see in subsequent lecture we will try to derive the equation of motion of this kind of disk without considering the gyroscopic couple, and initially we will take the 4 degree of freedom system and we will obtain the corresponding 4 equation of motion, that is 2 in the translational direction and 2 in the tilting. This particular tilting is different, which we considered initially in the case of the Jeffcott rotor, that was the torsional displacement theta we considered. So, in the present lecture, we have analyzed the Jeffcott rotor model in detail, even its solution procedure by a complex method and matrix method we have seen, so that we can get more insight into the method, how it works. Apart from this, I defined the wobbling motion when the disk is offset from the center, how additional angular displacements introduces in the model, and this particular model will be analyzing in the subsequent lecture. Thank you.